Let's see what we can do with this. So we have an inverted pyramid. It's being filled with water at a constant rate of 25 cubic centimeters per second. So let's pause there and think about that for a second. So it's being filled, constant rate, 25 cubic centimeters. So cubic centimeters, that's volume per second change in volume. So what did they just tell us there? They told us that the change in volume, dV, over time in seconds is always 25 centimeters cubed per second. So we have stuff flowing in at that rate, dV dt, filling this thing up. So this thing's slowly filling up. And as it fills up, right, the height is changing, and we're going to have this new surface area at the top as it's going up. So there's all kinds of things changing out right at once. The volume is changing over time. If we pause at any time, it's filled that much. So we have this new length and width there, and this new height vertically. So that B is changing over time, and the height is changing over time. So all these different rates are related to each other because of the shape of this object here. So what can we do with that? Well, we need to describe this shape mathematically to figure out how these things are related. And they give us a little more information. The top is a square, so B1 is equal to B2, and those side lengths are 3 by 3. All right, let's fill that in. So this is 3 centimeters there. That one there is also 3 centimeters. And the total height of this thing is 6 centimeters. And if you don't remember the volume of a pyramid, it is 1/3 times the area of the base, which would just be for us b squared, times the height. That's the volume of a pyramid there. Now we have too many variables going on here. So we're gonna usually wanna whittle it down to just 2 variables if possible. So I'm gonna try to do that next. So bottom line is, geometrically speaking, we have some similarity going on here, that this red pyramid I drew down there is the same shape as the big blue one right there. And so how are those related? Well, the cross section of this is a triangle. And the big version is 3, and then the height from here to here is 3 by 6. And then at any particular time, we're going to have a smaller version of that. I'm just going to call that B, and then we'll call this H right here. And these are similar triangles. So the base over the height is always going to have a constant ratio. So it's always going to be 3/6, which reduces nicely. Not always, but this one does, right, to 1/2. So that means let's see, the base is always half the height, right? We multiply the height to the other side, and we get the base is always 1/2 of the height, or the height over 2. All right, so that means because we have this shape, it's always the same shape, it's always this shaped pyramid, we can simplify that volume now. So the volume can be rewritten. Instead of a B, we can have an H over 2. So we get 1/3 H over 2 squared, right, times H. That cleans up a bit. H squared times H is H cubed. 2 squared is 4 times 3 is 12. So I get H cubed over 12. So that's my V. Now I want to, and then you might ask, well, why did you solve for B in terms of H instead of H in terms of B? And my apologies for not mentioning that. My brain read this before I read it out loud. Right now, find the rate at which the water level is rising. Okay, so they're saying water level is rising. So they want to know that rate. So they want to know what's dH dt here when the height is equal to 2. So that's why I solved for B in terms of H here. So good advice. Read the whole problem, then go back and start breaking it up. All right, so now that I've got this simplified down to just the two variables I care about, and again, why do I care about these two variables? One, I was told dV dt is this constant of 25 centimeters cubed per second. And then two, I was told to find the rate at which the water level is rising, which is dH dt. So I needed a formula related to the shape of this object here that relates the volume to the height. So I got that. Next, I want another formula that relates the change in volume to the change in height. So that's where implicit differentiation comes in. The new twist here is we're differentiating with respect to time, right? So both volume is a function of time and height is some other function of time. And according to the chain rule, I have to, whenever I see a function within a function, like h is a function that's being cubed, I have to use the chain rule there. So if we want to find the derivative with respect to time, we're going to implicitly differentiate on both sides. So I get derivative with respect to time on both sides, and derivative respect to time of volume, that's just dV dt, nothing much happening on that side. On the other side, the 1/12 is just hanging out because that is a multiple, right? 1/12. And then the h cubed has a derivative of 3h squared. But since h is a function of time, I have to multiply by its derivative, which I'm going to call dH dt. And now I have a relationship relating the change in volume to the change in height. And in this case, we want to solve for the change in height. So that means I'm just going to divide that sucker to the other side, or maybe multiply by its reciprocal. Let's do that. So dH dt is equal to dV dt times 12 over 3h squared. And I guess I should have cleaned that up ahead of time, huh? Let's back up just a sec. A little algebra here, always in our best interest. 3 goes into 12 4 times. So h squared over 4 on this side becomes 4 over h squared. And I'm asked to evaluate that when the water level is 2 centimeters. And so since there's no more b here, I don't even care about what b is at that point. I only care about what h is, and I know what dV dt is. So if I evaluate that, choose a new color here, when h equals 3, then that's going to give me dV dt is 25 times 4 over 3 squared. And nothing cancels there. 4 times 25 is 100. So I get 100 over 9. And let's double check the units there. 25 is centimeters cubed per second. 4 has no units, but the 3 did. The 3, ooh, why did I do a 3 there? It's supposed to be 2. Oops. Thank you for pointing that out. All right, let's try that again. Let's erase maybe a little bit. So that's not a 3. It is a 2 squared. I'm going to change color here. 2, h is 2. There we go. 2 squared is 4. Wow, look at all this cancellation. This problem gave me very nice numbers. So it looks like I just get 25 there. All right, now double checking the units, that's 2 centimeters, which I squared. So I get 1 over centimeters squared. Centimeters cubed over centimeters squared is centimeters. Seconds is still hanging out. So the units of this number should be centimeters per second, which is what the change in height over time should be. Cool, units work out. So I get 25 centimeters per second is the rate at which the height is changing when the height is 2 centimeters and the volume is constantly increasing at 25 centimeters cubed per second. Related rates, fun stuff.